Welcome back. Thank you for sticking with us. And in a change to our published schedule, Lynda, who we skipped earlier on so that everyone could get something to eat, is going to give her talk now. So over to you, Lynda.
Yeah. So I'll be presenting. Hello, I'm Lynda. I am a PhD student at Queen's University Belfast under the supervision of Andrew Brown and Gabriel Granveau. And today I'll be presenting some work looking at the resonance analysis of strong field ionization. This is work that we did in collaboration with the experimental group in Heidelberg, Germany, led by Christian Ott. And to start with, I'll go through some results that were recently published at the end of last year in this paper here, and then I'll go on to talk about what we've been working on since. Max was the lead in experiment, and I was lead in theory. That involved running some RMT simulations, or R matrix with time dependence. Hugo gave a really good overview of RMT on Wednesday, but I'll give a brief overview here just so we're all on the same page. So the goal of RMT is to look at laser matter interaction, and the way we do that is to solve the time-dependent Schrödinger equation without making drastic simplifications such as modeling a single electron or using a one-dimensional system. We solve the time-dependent Schrödinger equation for a field multi-electron system in field 3D. The way we do that then is if we consider the time-dependent Schrödinger equation as a partial differential equation, then what we need to solve it is the initial wave function psi and the initial Hamiltonian. To do this, we borrow techniques, or rather codes, from traditional atomic, molecular, and optical physics, which solve the time-independent Schrödinger equation. So we get a really good detailed description of our wave function and our Hamiltonian. Then we propagate these forward in time, taking account of the changing potential, that is the laser and the rearranging ion at each time step. So from this, we get our time-dependent wave function, and from the time-dependent wave function then, we can calculate our observables. In this work, the observable we were looking at was attosecond transient absorption spectroscopy, or ATAS. And this is a powerful two-color pump probe tool, which is used to study electrons on the attosecond timescale. And typically what you get from ATAS is an absorption spectrum which looks like this. So we're looking here at the resonance energy of about 55.4, and you can see we get a nice absorption line from this. What's really nice about ATAS is because it's two-color, and we can have time-resolved investigation. So we can vary the time delay between our two pulses and look at how things change over time. So we can start with something that looks quite Lorentzian, and then as we change the time delay between our two pulses, we could end up with something that looks quite Fano. And a Fano profile is indicative of some interference which is happening. What's really nice about ATAS is that the observable is not an electron, so we can look at processes such as strong field ionization with it. We looked at xenon in this work, and our setup was as follows. So we have our neutral xenon, and we have an IR pulse, which comes along and ionizes an electron from the valence shell, so we're left with a hole in the 5p shell. Then we have our second attosecond XUV pulse, which comes along and promotes an electron from the 4D shell into this 5p hole, and then what we're left with is a hole in the 4D shell. And it's this transition that we're going to be looking at in this work. Then by varying the time delay between the XUV and IR pulses, we can look at how these things are changing over time. This animation is flawed, so really what we do is we keep the XUV fixed and change the IR, but it's easier to move a small thing about a screen than it is to move a big thing. So doing that in both experiment and running lots of calculations, we end up with a 2D color plot that looks like this. So here we have our energy on the x-axis and the time delay on the y-axis. And you can see that we get really nice agreement between RMT and experiment before we even dive into the details. So you can see as we move, so our energy we're looking at is about 55.4. And you can see as we move from time delays where the XUV arrives first to time delays where the IR arrives first, we get this absorption line building up. And that's what we expect because we need the IR to come along and strong field ionize to create that hole in the 5p shell for the XUV then to promote a 40 electron into. So that's what we expect. So when the IR arrives first, we'll get a good absorption profile because we'll have the hole in the 5p shell for the XUV then to promote things into. Looking at the individual line outs then, when we look at time delays when the IR arrives before the XUV, we get this nice Lorentzian line profile. But when we look at time delays where there's an overlap between the two pulses, or when the XUV arrives first, we get something that looks quite Lorentzian. So we've got some sort of interference going on here. What we propose then is that we have a second pathway. So in this pathway, when the XUV arrives first, it excites to some virtual excited state, and then the IR comes along and ionizes an electron from the 4D shell. So we've got the competition of these two pathways in our system. To kind of confirm that this is exactly what we're seeing, we look at the line shapes in more detail. And to do that, we perform a fitting procedure. So the fitting procedure, the equation we use looks like this. And what's important here is there are 3 fit parameters which are important. The first is the line strength, or the height of the peak. The second is the line width, or the width of the peak. And the third then is the phase, and that basically describes how Lorentzian or Fano your profile is. And a phase of 0 corresponds to a Lorentzian profile. So performing these fits for all of the time delays that we have in our time delay scan, and also for several different IR intensities, we end up with this. So this here is the strength fit parameter, or the height of the peak, plotted as a function of the time delay between our two pulses. And you can see this is kind of what we expect. So as we move from time delays where the XUV arrives first to time delays where the IR arrives first, our absorption line is building up in strength. And that's what we expect because when the IR arrives first, that's driving more strong field ionization, so there's more opportunity for this pathway to take place. And what we find here confirms the findings of this paper, where they looked at this in more detail. The other thing that you can see from the strength fit parameter is that there's these oscillations in the build-up, and these oscillate with half of the IR period. So the minima of these oscillations corresponds to the zeros of the IR field. In this paper, they call them overshoots. And this is basically the combination of reversible and irreversible effects. So you've got irreversible strong field ionization, which is the general build-up of these things. And then you've got reversible excitement to some excited bound state and back down within half the cycle of the IR. And that's what causes these overshoots. They looked at the strength in this paper, and we looked at the phase, so basically how Lorentzian or Fano the profile was, and we get this. And you can see that we get the same half cycle oscillations in the phase fit parameter as you see in the strength. And also as you go from time delays where the XUV arrives first to time delays where the IR arrives first, the phase tends towards 0. So we're getting less interference as we move to time delays where the IR arrives before the XUV. The third fit parameter is the width, and this fit parameter reveals the difficulties of the fit procedure at the negative time delays, or time delays where the XUV arrives first. And that's because we have a very weak absorption line, so the signal to noise ratio is quite high, so it's very hard to fit the line shapes at these time delays. So for that reason, in our analysis, we focus more on time delays from about -1 onwards. The other interesting thing from the phase fit parameter is that as you increase the IR intensity, so as you go from the purple lines to the yellow lines, the amplitude of these oscillations decreases. This was surprising to us at first because usually things scale linearly with laser intensity. So as you increase the intensity, things get stronger. But here we've got something that seems to be getting weaker as we increase the IR laser intensity. So this was something we wanted to look at in more detail. So we extract the amplitude of these oscillations. The way we do that is we take away the cycle average trend. So it's oscillating about 0. You can see that here. And then we just find the amplitude of these oscillations. And you can see this is what we saw in the figure before. As you increase the IR intensity, the amplitude of these oscillations decreases. Doing the exact same analysis for the experimental data, we see the same thing. So as you increase the intensity, the oscillation amplitude decreases, and we get nice agreement between theory and experiment. What I haven't shown here is horizontal error bars on the experimental data. There's an up to 10% uncertainty in the experimental laser intensity. So perhaps the agreement here is even better than it looks if I were to include the horizontal error bars. For this reason, IR intensity is maybe not the best parameter to look at this with respect to. So we can look at it from another perspective. RMT gives us access to the population left in the ground state at the end of the calculation. So this is the population of neutral xenon left at the end of the calculation as a function of intensity. And this is kind of what we expect to see. So as we increase the IR intensity, we're driving more strong field ionization, and so we'll have less neutral xenon left at the end of the calculation. And you can see at the highest intensities, we're driving about 80% ionization, so we're in a highly non-perturbative regime here. My experimental colleagues did some clever things, and they were able to get the same from their experimental data. And you can see we get the same sort of trend with the experimental data, but there seems to be a systematic shift between the two until you get to the highest laser intensities. This is explained by looking at the population of singly ionized xenon and doubly ionized xenon in the experiment, which that's singly ionized and then doubly ionized. And you can see from intensities of about 1.6 onwards, double ionization has a significant contribution, especially at these highest intensities. RMT doesn't yet account for double ionization, but we are working hard on it. So RMT actually becomes less reliable at these higher intensities, and that explains what's going on here. Really, there should be a systematic shift the whole way across, but because we don't account for double ionization, things are less reliable here. So looking at the same thing as before, so the phase oscillation amplitude, this time as a function of the ground state population instead of the IR intensity, we see this. So as we increase the amount of population left in the ground state, we also increase the phase oscillation amplitude. And doing the exact same thing then for experiment, we get really nice agreement between the two. And actually the Pearson correlation coefficient is almost perfect. There's almost perfect correlation between the ground state population and the phase oscillation amplitude. So how does this picture then help to explain our second proposed ionization pathway? Well, as you increase the laser intensity, you're driving more strong field ionization. So more population is going to follow this first pathway. At lower laser intensities, there's going to drive less strong field ionization. You'll have more population in the neutral ground state, and therefore there's more opportunity for the XUV to excite to some virtual bound state, and then the IR to finish the job to create a full 40 shell. So this kind of confirms what we proposed. And that's what we published in the paper. And in the paper, we call this XUV-assisted strong field ionization. Since we published this paper, we've been working really hard on getting some relativistic input data for RMT. So this time rather than having one transition, we include the spin orbit split states, and we get 3 transitions to look at. So we do the calculations, and for a full time delay scan, we get something like this. So rather than the 1 peak we saw before, this time we get 3, T1, T2, and T3. And the same in the experiment. So the experimental data I showed before was zoomed in on this first peak, which corresponded to the non-relativistic transition that we had before. But when you zoom out, you can see that they see the same 3 transitions in experiment as well. In the experimental data, you can also see the double ionization peaks creeping in here as well. So T3 in experiment is actually quite hard to look at because you've got the double ionization resonance lines at around the same energy. You can look at the same lineouts and you see the 3 transitions, some they're Lorentzian for some time delays and Fano for others. And since we've also been looking at a different way to consider the fit parameters. So we have a fit for the line strength and we have a fit for the phase. But if instead we consider the line strength as an amplitude, then what we have here is a complex number. And we can plot these things on the complex plane. So rather than having 2 separate plots as a function of time delay, one for the strength and one for the phase, we can have a single plot in the complex plane. And doing that, we end up with this. And this to me at first seemed a little bit crazy, but we can actually understand what's going on here. And what we have is some motion of the center point, and on top of that, we have some circular motion. Using a combination of 4 fits to these things, we've got a sort of preliminary model of the resonance dynamics going on. If you're wondering how these 2 things match up, I've got a little GIF, and basically the length of the black line corresponds to the strength fit parameter, and the angle it makes with the x-axis corresponds to the phase. So these are the 2, the same data represented in different forms. What to look at next, firstly, is to look at these complex plane plots and try to understand what's going on, both for experiment and theory. RMT gets a lot of things right with these, but we're really looking at the fine details here, and there are some differences between the experimental data and RMT that we need to find explanations for. The second thing to look at then is the relativistic picture, and comparing the 3 transitions, T1, T2, and T3, and how the behaviour of the resonance line changes between these 3 transitions. And what might be particularly interesting is the differences between T1 and T3, because they start at the same initial state but end up in 2 different states. And that's me. Thank you very much for listening. I'd like to thank my supervisors, Andrew and Hugo, and then also my experimental collaborators, especially Max and Christian, who've been very patient with a theorist.
Are there any questions or comments?
Thanks for the time. It's super interesting. So I have a question. When you do this RMT, we have full correlations, right? And you get such nice fits in agreement with the experiment. So did you try removing, like, to see the correlations or seeing, do they matter? For these fits?
We can't really remove those in RMT, by default includes everything. So that's something, if we had like simpler models, might be interesting to look at, but we just can't fix that with the RMT. It's by default, as Catherine said, hits the nail with a hammer.
You could close the 4D hole, but then everything would disappear.
Yes, exactly. Yeah.
Anything else? Then let's thank Lynda again. So the next item, I gave it a bit of a plug yesterday. So something a bit different. My colleagues here will introduce themselves in a second. But for context, at the minute, I am kind of, what do they call it, a jack of all trades and a master of none, emphasis on the second aspect of that. I currently hold a fellowship in what's called research software engineering. So this is something I talked to a number of you about last night on the boat. So how much of that you remember, I guess, is up for debate. And this concept of research software engineering has really kind of taken root in the UK, especially over the last 10 years. This panel really is just sort of introduce the concepts to you, a science audience, and to hopefully sort of get us talking about some of these things. Give me 1 minute to find my Menti Menti quiz, and then we can start with the discussions. So if you would mind, once again, joining this Menti poll, I'll try and make it single. There's the code. Oh, that's true. Thanks, brother. So, assuming that all of us, well, I'm hoping that all of us in the room, whether we are theorists, people who are burning through millions of CPU hours like Lynda, or even experimentalists. In fact, we heard this in one of the presentations yesterday about the importance of doing this kind of this analysis of experimental data. There's some code, some software involved in what we're doing. And just to sort of take a read of the room, we're interested in knowing, how do you make your code available? So I'm slightly worried because I know that myself and Hugo and Lynda are all in the room, and we make our code available in version control repository. So maybe that's the three. Okay. But this is interesting, and it's also kind of what I expected. This has been the de facto standard in the field over the last, well, basically for as long as I've been involved in it. And this is just, unless we kind of address this is probably the way it will continue. And so my hope today is that we can give you some sense of why this is an important issue, and maybe give some guidance on the kinds of things that are important in this field of research software engineering. So without further ado, I will end that, and we will not need the screen again. Allow me to introduce my colleagues, and they will then introduce themselves. So sitting immediately to my left, this is Neil Shu Hong. He's the founding director and still the director of the Software Sustainability Institute. This is Sarah Jaffa. She is a research software engineer here at UCL. And this is Tom Meltzer, formerly an RSE at Leicester, as of tomorrow, an RSE at Cambridge. So welcome to the three of you. And if we could start, could each of you just give us a little summary of your journey into RSE, including your background, where you came from, and Neil, if you would mind to kick us off.
Can everyone hear me at the back there? Yeah, it's good. I have been pretty much all my life at the University of Edinburgh. I trained as a computational physicist and then moved into what was there, a technology transfer center at the university. So I was working with small and medium sized enterprises to look at things like machine vision, expert systems, I guess you call them AI now, and all sorts of different sorts of software development. So I guess I was an RSE before, a research software engineer before research software engineering was coined. A lot of the first part of my career was developing software for other people who were trying to apply things that were being developed at the university in different ways, whether that was novel algorithms to do with trying to sort mushrooms, to working with big database companies to try and understand ways of making querying more efficient. So as a result of that, I switched over. I started going more into the management of software projects that are being done by research groups, and realized that there was something to be done to support all of these different groups and people. And that's where the idea of the Software Sustainability Institute came about. So for the last 13 years, we've been running the Software Sustainability Institute as an organization that supports people who use and develop research software. And that comes from all different fields, from from the work that you've been presenting over the last few days. And it's really interesting. I saw on that poll, there wasn't anyone who said, I don't produce code. So I think that's part of the really important thing to realize, is that we all use software in some way, and we all produce software nowadays, all the way through to the humanities, social sciences, and so on. I'll stop there though. I'll pass on to Sarah.
Hello. So 2 years ago, I was an astrophysicist. I started with a degree in physics, did my undergrad and PhD in Cardiff, where I started writing little data analysis scripts. I think as most people start coding, someone throws a lot of data at you and you go, I want to make pretty plots, or I want to calculate some basic statistics, and writing basically the same code that every researcher writes ever to do those very simple things. Moving on to my PhD was on data analysis of chaotic star clusters. So trying to find ways of describing star clusters using fractal dimensions and chaos theory, through which I published 2 tools that I thought, the entire community could take up to study their own star clusters. And I've written nice bits of code. Unfortunately, my supervisor's idea of the best way to deal with code was don't publicize it, don't put it on the internet, don't make it available to anyone. Because if they can get it without talking to you, they will cite your paper. Whereas if they have to talk to you, they will collaborate and you will be on their paper. The consequence of which was no one ever cited that paper. So for the second tool I produced, I did actually put it on GitHub by myself in my own time, because I couldn't take any time out of my PhD research to do that. But I made it available on the internet, and 2 people tried to use it and sent me a lot of questions going, this doesn't run on my computer. How did you make it work? What does this variable mean? When you have an input file, was that a text file or something else? Because I haven't actually explained how to use the thing I had published. Most of these had, published papers by the standard order of science and had succeeded, but that didn't really get very far in making the community use the things I've designed. In my postdoc, I moved to the University of Hertfordshire, where I started doing simulations of star formation. So using smooth particle hydrodynamics, which is a method of simulating giant clouds of dust and gas, smashing them together, trying to make stars, which basically involved someone giving me thousands of lines of C++ code, which I did not speak C++, and saying, run this. And 3 years later, I had not got it to produce a giant star cluster, and I had not published any papers, and I found it slightly difficult to apply for more science jobs. And basically at that point, having put myself through a lot of courses to try and learn computational skills, I think I actually went to one run by the SSI and found out that there were these people called research software engineers whose job was to help you with all of those things that I have just mentioned, making your data nice and tidy, making your code shareable and findable and usable by other people, making your simulations actually run, making them run faster and more efficiently, making them run on different computers, and making it so that you can actually share your results and your code in a way that other people can reproduce. And I thought that sounded like great fun. And I'm pretty determined that no other scientist should have to go through what I went through in my postdoc. So that's why I applied to the University of London, University College London. And I'm now been an RSE for about 1.5 years. Worked on 9 different projects with people from all over the university in different fields. And it's incredibly enjoyable.
Yeah, this is going to be okay. Right. So yeah, I was also a physicist. I did my PhD at UCL in theoretical physics, and my research covered electron collisions with atoms and molecules. I did some strong field stuff. I also did time independent work as well without lasers. So yeah, some of the talks today, it was nice to be back and see, someone mentioned non-sequential double ionization earlier, and that was what I did half of my PhD in. Then I went, got a postdoc position in Prague at Charles University, and I basically continued my research into electron molecule collisions. And actually, in kind of that process, like I realized I was loving more and more the kind of heavy, hardcore computational side of it. So we were solving, like everyone else in the room, solving Schrodinger's equation in many different ways, and we had the R matrix codes, and they were really well written, like kind of parallelized, and I got to use like MPI, OpenMP, and then things were coming up about, I think in Andrew's group you implemented the GPU stuff for your, or someone in Belfast. Yeah, so there was like talk about, you know, adding GPUs into atomic and molecular science, and that stuff really interested me. And I was just loving more and more computational side, and I started to think about long-term longevity of my career. Ideally, I wanted to be a postdoc forever, and that career just doesn't exist. Yeah, and it's some chuckles from the audience, but unfortunately, the way that the system is set up, the system, you know, of science and academia, becoming a full-time postdoc is rare. And so I realized then there's this avenue being, you know, research software engineer, which essentially ticked all my boxes. I got to do the computational stuff, still work with science, but effectively I can get a permanent contract. So there's a small plug in there for any sort of postdoc-y people that are thinking, oh, I like being in science, but I want to be more permanent, you know, and not kind of have all the responsibilities that come with becoming a professor or lecturer. And yeah, and then it's been really fun. You get to work on it. I'm kind of science agnostic. I don't mind which science field I work in, just as long as it's kind of furthering humanity in my own little way that I see it. So yeah, it's a nice place to be.
Okay, so there's been some ideas come through there already, but maybe ask the question more directly. Why should a room full of scientists care about this stuff? And maybe I'll go in the opposite direction. So Tom, I'll start with you.
Yeah. So yeah, a lot of the kind of computational skills I learned now came from sort of my PhD and postdoc. And I really realized the importance of good programming practice in specifically my postdoc, where we worked on a code that was collaborative effort. So there were people at UCL, there were people in Belfast, there were people in America, people all over the world that were using this code. And actually having it like, so do people know what I mean when I say version control software? Is that showing? So there's well, first of all, there's version control software. So that helps you kind of keep a infinite undo list. So like at any point in time, you can go back and see, oh, last year, these are the changes I made to the code. 2 years ago, these are the changes, you know, my postdoc made or my PhD student. So that's kind of version control software. And then there are different options, different flavors, but you can get hosted ones. So there's things like GitHub and GitLab. So if you haven't heard of those, they're just like kind of centralized a server somewhere that you can connect to by the internet, and that will keep a history of your code as well. And these become very important when you want to collaborate with other people. So we had this international collaboration, and the code was available to everyone. It didn't need, oh, I need to send an email to the postdoc in this group in Germany to get their copy of the code, download that zip, compare the files that have changed to my own version. It just gets rid of all of those headaches. So I think one of the first things I would say, like in terms of benefits, added value from research software engineers, we can kind of give some insight into like good practices to help your work life easier, you know, so you can collaborate with collaborators without having to like have the headache of comparing all these different versions. So yeah, I'll give one bit and then
I think on a very individual level, the benefits of learning better software practices is mainly your job is not writing code, your job is doing science. You know, your job is finding out how xenon works and solving Hamiltonians. And if you are taking more than half a day of your life struggling to install a piece of software or get some code to run or wait for something to compile, you are wasting your valuable grant money and time, and you should really be getting someone who has fully computer science training and software skills to be doing that for you. If you were working in a physical lab environment, I'm sure some of you do experimental stuff, and you have lab techs who run the machines or fix the machines when they're broken to help you. Like, science is a team sport. You need people who have different skills, and maybe at one point it was easy enough for every researcher to be writing their own code, but I think we've got beyond that point, and this should not be your problem. It should be something you are contacting other people to get advice on, because it's a waste of a short PhD or postdoc contract to be spending more than a day on that kind of stuff.
Yeah, I think one of the things that's maybe not always obvious is that in research, software often has a very long lifespan. You know, you've been probably working on some of your codes for years. There are other codes that have been going on for decades. And because of that longevity of the software that's used, it's really useful to be able to have some way of having continuation of maintenance. And it's very hard if most of the development work is being done by PhD students or on short-term contracts. So I think one of the things that research software engineers, RSEs, bring us is maybe going towards what we saw previously in the way of things like staff scientists, people who were there employed on contracts to deal with all of the more boring stuff sometimes of the work that's required in any research group or lab. And in particular for research software engineering, so much is changing quite rapidly around how software is being developed and the different tools that are being incorporated. We've moved from things like GPUs and accelerators now into a lot of people looking at how generative AI will be used to help with their science. So having people who can concentrate on some of that so that you can think of what that means for the science allows a collaboration to exist. And I think that's maybe the most interesting part of seeing it from both sides, both from as a researcher and also working with research software engineering groups, is that collaboration makes things better. And it's a bit like what happened in the biosciences as well, where we saw the growth of bioinformaticians. And in some of the other areas where we see the role of statisticians. It's another expert to be part of your research group.
So the other thing I would add to the points that have already been made is that there's obviously sort of personal incentive by being able to make your own life easier. There's a sort of community incentive in terms of enabling others to engage and get involved. But I think there's also then this sort of scientific incentive as well. We don't sort of realize that perhaps science is being hindered by the fact that Sarah said that we're sort of spending a lot of time doing this. And you said about how software potentially has a very long lifespan. On the flip side of that, quite a lot of software has a very short lifespan because we end up doing things over and over again because we don't have established tools or we're not aware of established tools, we're not using established tools. And so every PhD student has to write their own code to do the same thing. Potentially this is slowing us down. And for me in my own work, what I've noticed is that you spend maybe the first year of a postdoc trying to onboard somebody and get them used to what they're doing. And then they spend a year working on things and then they're looking for new jobs. And then you spend the first year after they've left trying to unpick all of the mistakes that they've made or fix the bugs, right? So there is a scientific benefit, even just in terms of this kind of continuity that you were talking about as well. So that's the best thing. Okay, so we've talked a bit about the incentives. Let's talk a little bit about what actually is involved in your jobs as RSEs. What should we be aiming for as a sort of gold standard, sorry, that's the next question. What are some examples of good practice in terms of software development? So not even just, getting somebody else to do it for you, which is some of what is being talked about, but what are some of the things that all of us could be doing to sort of leverage some of this, so Sarah, you're on the first one. So.
I think building on what you said about a lot of people writing similar code, one of the things I would really advocate for, even if you can't find a friendly RSE to talk to, is just talking more amongst yourselves. You are all very clever people, and some with more experience, some with less experience in these things. Code review might sound scary, but actually what it means is simply next time you have written a bit of code, whether that's data analysis or a simulation, give it to the person who sits at the desk next to you and ask them to try and run it without you looking over their shoulder. And then ask them how they struggled and get them to try and read through your code or your instructions and see if someone else can understand it, someone else can replicate your work, and equally see if they can then suggest changes. It doesn't have to be a very sort of combative thing, much as the quantum battles element of this conference does sound fun. Code review is about supporting the people around you who might know about a better plotting library or a better linear algebra library that someone just hasn't heard of before. We can just about keep up with all of the papers that exist in our own scientific fields. Trying to keep up with the advancements in computer science is a whole other thing we don't have time for. So being able to chat between you and go, oh, I just heard, have you tried using this analysis tool or this library that does some of this stuff for you, or something that has a slightly better way. You can just start discussing your code, start learning from each other, start trying to share this knowledge among your groups so that when you do get the one PhD student or postdoc who is really good at code leaving, all of that knowledge doesn't disappear with them, that you try and keep the knowledge going as you train up new scientists.
There's something to be said for making it part of science, right? Rather than just being this optional extra thing or this thing is taken for granted. I often say this to PhD students who sort of assume that you're going to learn how to give presentations and write papers just by osmosis, right? It's this idea that simply by being supervised by a genius like me, you're going to learn how to write a paper. But actually, we have to actively pursue those things. even if Lynda is a drawing. So Tom, you're next on this. You've already mentioned a little bit about version control.
Yeah, I really wouldn't like. So I worked in a couple of research groups doing my PhD, and then I worked, postdoc, and then as a research software engineer, I've worked with other groups and seen how kind of their code process happens. And I really would encourage everyone in the room, if you don't already use a centralized version control system, something like GitHub or GitLab or Bitbucket, definitely integrate that for your group, because it pays dividends in time savings. So, for instance, Sarah mentioned code review, and that can happen naturally as part of these version control softwares. And there's so much wealth of knowledge in the groups. Like I was in a small group when I first joined, and it had like 4 PhD students, and that was it. There are smaller ones, obviously, but we had 4 PhD students, one that was nearly finishing. And when I started, and I was like first year, unofficially, he was kind of code reviewing my stuff and helping me and giving me lots of advice. But like having that documented in these version control software programs like GitHub, GitLab, it would then be available to anyone else that kind of searches that question. And when I use publicly available codes that are hosted, I'll often go to their issues section and be like, oh, I've got this issue. Someone's probably already solved it. And for big, mainstream packages, someone already has. Like the amount of times I get an error code, I literally just copy and paste it into the issue tracker. And then I find someone's been like, oh, you just need to do this. Brilliant. So I think code review is very important, and it doesn't have to be as formal as it sounds. It can be as simple as a postdoc or PhD student just going, yeah, that looks good to me. So I think having that is great. And then the other thing that's really good is, and so I mentioned a little bit about use existing libraries. I used to kind of think it was cheating when I was like a PhD student. I used to write everything myself. And the amount of times I've worked on codes and seen people write matrix multiplication routines, just don't do it. If you're doing something that involves linear algebra or kind of integration, differentiation, something like that, someone's already done it 100%. And you're not going to beat the efficiency of like 30, 40 years of computer scientists hacking away at optimizing the assembly code so that it's faster. You're just not going to win. So learn. I think in a sense, I joke sometimes my job's about kind of being a good Googler. Like I know where to look for the right answers quickly. And the same as a scientist, physicist, you'll know where to search for certain answers, certain papers. Kind of learn, get a vocabulary for looking into different libraries, and that pays dividends, because you can just borrow from this library for that. There's a statistics library, a plotting library. Like, don't do these things yourself.
Yeah, you remind me of so you sort of say Google. When I started my career, we didn't have Google, and so for me it was typing out things from numerical recipes in C and numerical recipes in Fortran. But even so, it's kind of like that is code reuse, and I completely agree that one of the big things is when you look at developing things, 95% of it has already been done, and what you're trying to focus on is that 5% where you can bring value. So if you were someone, so I was using a library that I partly use because of the name, called Fastest Fourier Transform in the West. I was not someone who was good at Fourier transforms and implementing code to do that. I was looking at it to apply it. So it was terrible. I didn't need to write that code, although at one point I did try and write Fourier transform code. It ran really badly. Don't do it. So yeah, reuse libraries. I think the other thing that's connected to that and is really much better now than when I started is the tooling around software development is so much easier to use. There are lots of great different development environments, things like VS Code and so on. So I started off I didn't use VI. I was the other side. I was more an Emacs person. But yeah, there are lots of things that help you integrate your editors with your debuggers and so on, so that it becomes easy to write code and becomes friendly. I really love notebooks just now, like Jupyter notebooks, because it suits my style of experimentation, of trying to work through an idea before I create a more optimized version of the code. And so find the tools that work for you, and find the tools that work for your collaborators and groups as well, because it's much easier to do things like code review and version control if you have some agreement on the tools that you're using, a lot of them are interoperable. Some of them aren't. so yeah, it's good things. And the other thing I'll make a quick pitch for is a lot of these things, code review, version control. You mentioned a course. I wonder if it was a carpentries course that you did. So there is an organization called the Carpentries that does openly licensed training for researchers in software development and data management skills. There are courses run all over the world. It's run on 7 different continents. And in the UK and Europe and America in particular, there are courses running nearly every week. Almost all of them are free or cheap to attend. So if you have researchers that you know about that are looking to learn some of these skills, send them on a carpentries workshop. It's a really good start for learning what you need to know. I kind of say, it's the equivalent of learning how to change a tire on a car. You're not trying to become a mechanic. You're not trying to become someone who's developing the next Facebook or kind of Google. You're wanting to know enough about it so you can talk to RSEs, and enough so that you can do the easy stuff yourself rather than having to go into a garage and then paying, they're charging you lots of money to change a tire or change a light bulb.
Yeah, that's a good tip. But the carpentries course, that was my sort of way into this as well. And actually, after the workshop, I'll be circulating some resources that we've compiled, basic links. So Tom said about being a Googler. I'm going to save you the hassle. I'll send some resources around, so that just to make you aware of some of the resources that are available. So we talked a little about the easy things that each of us could be doing. But obviously, if in your sort of dream, like what's the sort of gold standard that we should be aiming for? Tom, start us off.
Yeah, some tests, write tests for your code. It's the last thing that anybody wants to do. You've got, research deadlines, funding deadlines. You just want to kind of get your stuff done. But again, tests is another thing that will actually save you when you need it the most. So it will be just before, your paper comes up from review, you say, we're just going to rerun these calculations and just check this. And then you add a new line of code thinking, it's just going to fix this bit, right? And then you don't realize you've broken half the rest of the code, and then you're going to figure that out the night before you submit. And like these things, write as many tests as you can. And I know some people think, he means unit tests now, I'm going to get scared, we don't have time to unit test all this legacy code that's like 30 years old and written in Fortran 77. You can start, the easiest way to get into it, I would say, is write an end-to-end test. So that means your code, given some input, whatever it is, you might say, here's this laser pulse and this atom. You run it and you get the final result that you'd say you used for a paper. That can be an end-to-end test. So you save those inputs, you save the outputs, and you say, okay, when I run my code, this is what I should get, okay? Then if you make your changes and you think, I'm just going to modify it so it also works for helium, it shouldn't break hydrogen. It should still work for the first atom or molecule you tested. So having an end-to-end test, at least to make sure you're not breaking historic, the output you used to be able to produce. But obviously, the more tests you write, the better. You're never going to write bug-free code, ever. Like, you're always going to have bugs. It's not possible as far as I can see it. So it's just another layer you can add in to protect yourself from like shooting yourself in the foot with a schoolboy error or like a simple mistake that could otherwise be avoided. So
I think one of the really valuable things is if you are the PI on a new grant, setting up your study, you're going to get funding, talk to an RSE at the start of that process. Don't try and come to an RSE when you've got 6 months money left and go, we just want you to optimize this and it needs to be done by next Tuesday, thanks, bye. Research grant funding bodies have actually said if they get applications now that have heavy computational aspects, if you're doing some high performance computing, simulations, data analysis, and you have not talked to a research technology professional about that, that shows that you don't understand how long your work is going to take. You have not properly costed that. You have not understood your structure of your work. You need to talk to someone who understands how long it's going to take, how much money it's going to take. Is what you've said actually feasible? I have definitely worked on grants where people have said, we're just going to run it on an Excel computer by the end of our grant. And if they come to us, we would have said this code isn't actually suitable to run on an exascale computer. That is a nice word. It gets you grant funding because it sounds cool. That's never going to happen. If you had asked someone at the beginning, we could have said, we could optimize this code to be moved towards an exascale computer. You can still put those things in, just make them more realistic, so that whatever then for PhD or postdoc you throw at that task is not completely fair. So yeah, that's my thing, is just when you are planning your work, talk to an RSE about the computing aspects of it. Just ask their opinion. We're very happy to review things, give you time estimates and budgets.
I mean, I guess this comes back to one of the first things that we talked about, which is just making conversations about software and code part of what we do with the samples.
We need to acknowledge that this is part of our work.
Yeah.
It's just as important as any other part.
Neil,
Yeah, and kind of following on from that, I think one of the things that I see is that the way that science is being done has been changing over the last few decades. And we no longer have this idea of the kind of hero science with a single PI and a set of interchangeable PDRAs and PhD students that are just a production line. What we have is collaborations. We have collaborations across groups in lots of different countries. We have collaborations with different specialists in the teams. Just looking at the presentation that came before, you sort of saw in that author list that everyone had a different role, and those roles were specialized. And so think about, in terms of gold standard and practice for doing better research software engineering, part of that is also recognizing that there are many different aspects to a great team. So you've heard kind of the sort of the software engineering part, but you also have to think about how you work to document all of this, the work that you're producing. You have to think about how you run the infrastructure and who you need to understand what HPC resources you need or what experimental resources you need. And things like community and mentoring as well, because in some sense, the gold standard is having everyone else in your area being able to use your software to do their research. And that takes a lot more than just good coding. It also takes really good engagement and mentoring. So yeah, that's my goal.
So I spoke to somebody on the boat last about this, and this is a topic that we sort of had listed under this heading, but I haven't talked about it really yet. The first question we asked was how people make their code available. And the overwhelming response from the room was you put this tagline at the end of your paper saying code is available on reasonable requests, right? And I put this to somebody last night, or not here, that's why we had a conversation last night. And he said, but why should somebody else get the credit for what I've done, right? And this is certainly a pushback I've heard from scientists who I've worked with. I've put all the effort into this, so why should I make that available to other people? Surely if I keep this as a very powerful tool that I have for my own career development or my own scientific reputation, whatever. So I don't know, do any of you have anything to say against that, Neil?
I have some maybe strong opinions on this matter. So let's take a philosophical attitude first. Why do we get into doing science? We get into science because we want to make discoveries, we want to change the world for the better. And in some sense, we do that because we share, we build on the knowledge and outputs of others. And software is one part of that. However, that's the altruistic viewpoint. The much more selfish viewpoint is that we develop these things so that we can get citations, so that we can build our reputation, and so that we can get promoted. I mean, everyone wants a better life and a better house. So the thing here is that our incentive systems are a little bit broken here with software. However, there are a number of studies that have been shown in different areas. Astrophysics is one, they've done it for the life sciences. There's been a study done for the geosciences as well, that when you share your code and your data, you actually get more collaborations, you get more citations, your reputation grows. So whilst there may be lots of reasons why you may not be keen on open science more generally, it is something that is an evidence-driven fact that your amount of reputation increases when you start sharing your code and data. And the other thing here, I think it's kind of going back to what you said, Sarah, earlier, is that if no one sees it, then no one can really collaborate with you because they don't know whether it's worthwhile collaborating with you. probably because they might not even read the paper in full. So being able to have that that kind of extra information to help them decide whether they want to collaborate with you is a good idea. And people get worried about being scooped. It does happen, but when you look at across all of the work that's published, being scooped is a relatively small. I think it's a very small fraction of papers and code gets scooped. So we could also flip it around and say, what I would love for you to take out as the one thing to do is that if you are reading a paper that you find interesting or you're reviewing a paper, ask to see the code. Just go and sort of email and go, can I see the code? Can I see the data?
Yes. Make that reasonable request that
Yeah.
they're asking you to make. Yeah. Tom?
I have a quick comment I want to say on this, and I'd like to see people raise their hands, right? Because I think so a lot of people are afraid that I put my code online, tomorrow someone's going to download it, reproduce my research, and get more papers, right? Does anyone here think that if someone else looked at their code in the room, they'd be able to run it? give them a week, right? No notes, no nothing. If I download your code tomorrow, do you think I'll be able to run it? Raise your hands if that's true. Because I've never seen that be the case. And if anyone can tell me, yeah, they had a new PhD student, they sent them the code via email, and then the next day they're like, yeah, here's the calculations I've run. Here's a paper. It's a fear that we all have, and I just don't think it's even realistic to have that fear. It took me the first year of my PhD to learn how to use the UKR matrix codes with documentation and with like all the code given to me and meetings with postdocs and PhD students. These codes are so complicated and so customly written for your niche of research. It is extremely unlikely that anyone's going to be able to just download that, copy it, and run it. So that's one of the things I wanted to add to that. I think we have this fear. It's incredibly irrational and non-realistic, in my opinion.
Sarah, anything to add?
A couple of things I scribbled down here was basically you could say the same about any paper. Like we all talk about our research, you give presentations, you've got preprints online. If you haven't published that work in a paper yet, why aren't we scared that people are going to scoop that? And the answer is because everybody knows, like, A, we have a sense of community and people are fairly responsible. And also everyone knows that if someone publishes that work before you, you can go to the editors of the paper and say, look, I gave this presentation. There were 100 people at this conference. This is my work. And I can tell you, I thought that I did before they did, and I've got documentation. And their paper will be retracted. We have systems built for this. The same is for code. Once you have shared your code on GitHub, once you've presented it at a conference, you can publish your code as its own paper, and you can do that before you share it. So there is documentation out there that this is yours. And if someone else uses it, just like using your research, just like basing a paper off your work, they have to cite you. That is the structure we've set up. If they're using your code, it's the same as anything else. They have to cite you or they have to collaborate with you. We've already got those incentives in place. People can't just steal your knowledge. They build up your knowledge. That's what we all do. And the other point I wrote down was, if you're not actually going to explain what you've done and explain how you've done it, why should anyone believe your results? There is a reproducibility crisis in science. Any other, like the whole point of writing a paper is to describe your method, that you have to describe, your experimental setup, like maths well enough that a peer review can say, yes, this person has actually done this work, and I believe their results are true. You should be doing the same with your code. Someone should be able to run your code, get the same answer as you. Otherwise, on peer review, they should say, I don't believe these numbers. I don't believe this person did this experiment unless I can repeat their results. Because that's the only way that we confirm that anything is true by more than one person doing it. So people should use your code and repeat your work exactly, and then give you credit for doing it.
Well, I'll just add into the mix that some of the fear in publishing code might not have anything to do with being scooped. It might be the fact that you're worried that somebody might find there's something wrong with your code. And in talking to colleagues, this is a real fear. Like this worry that you kind of put yourself out there and actually somebody finds these problems. And I guess the pushback against that is better now than after you published 15 papers based on the faulty code.
I have a little terrifying story about that. I don't know if anyone heard a couple of years ago when they found phosphine in Venus, and they think this is evidence for life in the clouds of Venus. And that was a huge deal. That was like publicized across the world. The person who published that paper put all of her code online, including the package she used to do like data cleaning of the astronomical observations. And someone found errors in that. There was a huge pushback against her work. She was hugely criticized in the community. It was really horrible. But she also pointed out that error wasn't in her code, that error was in a code she was using, which thousands of astronomers have also used. Everyone who published that code has that same error in their work, and no one had spotted it because no one had looked at that code thoroughly enough, because it is emailed from one person to another, it isn't shared publicly, and it isn't worked on by one person. Those errors are already in your work. It is better to find them before you publish than after.
That's good. Okay, I'm conscious of time and the fact that I started the day by promising that nobody would miss their plane, just like nobody missed the program yesterday. So I just wonder, are there any questions from the audience, any comments, anything you would like to know about before we wrap up? If not, I've got one more question to ask. What I did.
Maybe just a quick comment.
Sure.
So I think so you probably said that the reviewer, so like let's say if I'm reviewing some paper, so I should ask the author like for the code, something like this, is it? Yeah. So then the author will know right in the review, right? That will create some problem in the future if the paper is rejected.
So it partly also depends on your opinion of open peer review, but you can do this through the through your editor as well. So you can request that the editor passes on that if you want to remain anonymous.
It's the same way you submit your feedback. So you just write, I would like to see the code so that I can review this. Yeah, and again, you can choose. There are some benefits to being open peer review, but I get it. I was a PhD student. I didn't want to do that. I was postdoc. Yeah.
The code also they should be
Exactly. And this is something I push back on in
Yeah.
peer review, and I'm
Yeah.
not saying how often I've done it because there might be suffered as a result of that. But yeah, you push back through the editor and basically say, I will accept this once I get to see the code and make sure that it works. And yeah, and same thing. It's not just about getting the code. It's not just enough to make it available, but also structure.
And that's becoming a very normalized practice. I'm a journal editor in my field. It is perfectly normal practice now in that, and we're working with a number of other journals and publishers to kind of provide guidelines for how this is dealt with. So yeah, it's become a lot easier because editors are now more aware that people are looking for this, and that supplementary materials, code data really should be provided rather than being hidden away.
Any other comments or questions? Yeah. Okay. Let me ask one final question of each of our panelists then. So if there was one thing, if our audience members would take away just one thing from today, what would you want that to be? Sarah?
I would say talk to your local RSE. You might not have one in your group. You might not have, they're called embedded RSEs, people who work in a specific field. You might not have one in your university or research institution, but you do have access to these people through the SSI, through national organizations. We have the Alan Turing Institute. If you work with sort of national scale supercomputers, you might be able to get an RSE to consult on your work through there. I know DIRAC have them available. There will be people you can talk to, and even just a half-hour chat. You can show some code, you can talk about the problems you're having. They can just, as Tom said, we're better at Googling. We just know where to put you at the things you might need to know, and then you can go and get on with your work. And just please come and talk to one of us.
Yeah, and as a plug, I think the Software Sustainability Institute offer a sort of free code review service. Right? So, and
Yeah.
that's one of the resources that is in the sheet that I was sent on. Tom?
Okay, mine, I'm going to repeat it again. If you don't have version control of any kind set up, please do, and you will thank yourself when you accidentally delete your code and, you know, whatever, you can't find it. So version control, please. Thank you.
If you find yourself in the position I was at near the end of my studies where you realized you liked working with the software more than you liked the subject area, or kind of just want a bit of a break, then be aware that research software engineering is now a career path that you can take. Across the UK, there are so many different RSE positions that are being advertised. We cannot get enough skilled people who are interested in doing software and working in research. So yeah, there is a career path for you now that didn't exist when I started. And if you want to find out more, the Society for Research Software Engineering maintains a list of all of the job adverts that are open across the UK.
Thank you everyone for your attention. Let's thank our panelists and we'll move on with the rest of the group. Thank you.
Okay, so without any break, we will start the last session. The first talk by Lidice Rodriguez. Right? Okay, forward and hybrid path integral approach.
Sorry, I moved. Can you hear me? Yes, that's good. Okay, good afternoon, everyone. Thank you, Carla and Andrew, for letting me be here again. Today I will be presenting part of the work that is has been done together with these collaborators in my group. And quickly, I will talk about the oh, no. Okay, good. So, motivations for what we do, I said already during the battle, like we want to model the phenomena that we observe when we make a strong laser pulse interact with the atom. We need to solve the time-dependent Schrödinger equation, but we know this is challenging. So in the community for many years, we have been using approximations. And I will choose to present just one way, one direction of this approximation, which is the strong field approximation, and the things that the methods that go beyond the strong field approximation. And I would like to talk today in particular about one, which is the Coulomb quantum orbit strong field approximation that was developed by Carlos Maria and thank you. So quickly, I will go through the theory. Andy talked about this yesterday, but it's not here now. So in the strong field approximation, this is the transition amplitude that we get with the saddle point using the saddle point approximation. And we get this set of saddle point equations. This one will give you the ionization time. And these two equations, they will tell you how the electron propagates in the continuum. And something we can do in this action, we find integrals that the method that is typically used is to split the integral along two contours, one parallel to the ionization, to the imaginary axis. And this is what we call the tunneling or on-the-divided part of the action. And another one which is along the real axis, which is the propagation part of the action. And this is the form of this action, just to show you that we have the Coulomb potential during the under the barrier part and during the propagation part. And how the CQSFA is implemented. One important thing you need to understand, and this is what makes CQSFA different from other methods, is that it's implemented backwards. You know what you have at the detector, like the final photoelectron momentum distribution, and you want to know what you need at the beginning in order to have this final photoelectron momentum distribution. And to do that, we need to know what the orbits will do, and what they have been using for many years is this orbit classification that was introduced by Bauer, and this is for a monochromatic field. This is the four types of orbits we can get. And this has a huge advantage, is that to get the holographic pattern, we only need 4 orbits, one of each type. But the disadvantage is that it's not flexible. We change the field, we change the problem, then we have to change everything. So what we wanted to do is to use the CQSFA, but try to modify the implementation so we have something more flexible. And we developed 2 approaches. I will be talking about only one here today, in which we start from the CQSFA action and we build the rates. This is what the standard power propagation methods like semi-classical cluster model, quantum trajectory, what they do. And the main difference that we have with the implementations of these methods is how we calculate the rates. We approximate the rate from the tunneling part of the CQSFA action. And this leads us to one term, which is a non-adiabatic part of the rate, which is has been already published here, and one correction that we get analytically doing some approximation that were already proposed by Andy in this work, and we get something that we call a non-adiabatic Coulomb-corrected ionization. And we then implement the forward version of the CQSFA if you want. So this is quickly the model. We use a soft hydrogen atom with a soft core Coulomb potential where the softening is as small as possible, and this is the shape of the external field. And the first question we want to answer is how the Coulomb correction that we added to the rate will affect the initial distribution of the electrons once they are ionized. On the left, you can see the density plots of the ionization rate as a function of the transverse momentum. I didn't mention that, but we have a two-dimensional problem. So I will be talking about the direction perpendicular to the field and along the field polarization. So this is the direction transferred to the field polarization, and this is the laser index. And we can see that when we add the Coulomb correction, that's the CC there, the distribution broadened along the transverse field direction significantly, and we have a small narrowing along the laser phase. Next, how this will translate in the photoelectron momentum distribution. Here I'm just showing a zoom of the photoelectron momentum distribution. We observe that the holographic pattern that is mostly affected by this Coulomb correction is the band that gets a little bit elongated when we include along the transverse momentum axis when we add the Coulomb correction. And why? If you don't know, I tell you because I didn't know that when I started, that the band is a result of the interference of what we call orbit 1 and 2. So why is the Coulomb correction affecting these two orbits? We look at the single orbit momentum distributions. This is for orbit 1 and this is for orbit 2. And when adding the Coulomb correction, we see how the distribution along the perpendicular axis is elongated. And also, something interesting we found is that compared with the CQSFA results, the CQSFA, remember, we restrict the orbits. And when we do the forward propagation, the CQSFA only corresponds to the inner part of what we have for the single orbit distribution. We do the same analysis for the orbit 3 and 4. Again, CQSFA only captures this part of the single orbit momentum distributions. And something interesting we found is that the Coulomb correction doesn't seem to be affecting the distributions of orbit 3 and 4. And we get some interference within the same orbits, like in orbit 3 and 4, you can see that there is contribution from different types of orbits that we still classify as 3 and 4. And this is telling us that the restrictions we put on the orbits from the standard CQSFA, maybe they are too much, and we need something more flexible because we are missing part of the physics. And then the next thing is we went for a momentum map. Still, we want to understand why the broadening mainly on the fan, the holographic patterns. This is the result for orbit 1. I don't tend to show all the orbits, but this is the standard CQSFA, initial momentum for orbit 1 and the corresponding final momentum. And this is what we get with the forward propagation pattern. And the main difference you can see in the initial momentum is this structure in the low momentum region that is not present in the CQSFA. And if you compare the final momentum, you can see that there is this high energy rescattering ridge that is not present in the final momentum of the orbit 1 for the CQSFA. Also, if you look at how far away the initial momentum of orbit 1 is going, this is an indication. This is, and we have something similar for orbit 2. This explains why the span is the most effective one, is the holographic pattern that is changing the rate, because it expands along the transverse momentum axis longer than what we get for orbit 3 and 4, which unfortunately I don't show, but usually didn't. I can show them afterwards. So we wanted to understand why to separate the orbits according to the dynamics. So we implemented this filtering, which was already proposed by Maxwell in this previous work, where we say, okay, if the orbits, they are always beyond the tunnel exit, we classify them as non-colliding orbits. If they get between the Borg radius and the tunnel exit, they are sub-colliding, and if they go inside the Borg radius, then they are hard colliding. And we apply this to orbit 1 again. And this is the initial momentum, and this is the final. So you can see that what we call the non-colliding orbit one is the one that resembles the CQSFA initial momentum, and we get some soft colliding and some high colliding orbit one, and the high colliding ones lead to the scattering rings. And in particular, we learned that the inner region in this this region here, this one, is the one leading to the packet scattering rings. So conclude, the main message here is that we have implemented forward the version of the CQSFA where we use rate use the CQSFA formulation, and we study how this block of effect we derive the rate they are and this time we finish.
Thank you, Lidice. Some of the spectra are really artistic. Questions? Please.
Yeah, that's like a comment. So I saw the software position you were parameter, which is very specific 826. So how does it depend on that parameter? So
Thank you for the presentation. Actually, but we realized that we increase the parameter is previous year they are lost. They don't close. So that's why we should what possible. What we are trying to do now is understand what we learn that
Computational time, comparing forward and backward.
Thank you for that. If you the PowerPoint is into the page, what cannot be my goals so days that I and the security page. 1 hour. Yeah. I hope.
Because one remark is that we went backwards not only to but with what everybody did. Because people working on start the metro or experience among the last group or several people who have power they went for the forward program. And we started from boundary program. I don't know why, but we said, okay, let's try this. So we can find a way to define a function we can match with the practical condition. It makes it much less expensive, but at the same time, it makes it less flexible. And our aim of developing this was to get flexibility. And we were frustrated that we had to do like everybody else, get like 10 to the 8, 10 to the 9 to get convergence of it. But that was live. And one thing that you can see as well is that it's behavior that we have on this one sheet before. They are not actually impacted as we get over. So this is a big message from this important. But if you would like to give us some help, we are there because we have other things planned and we need to optimize that. Cheers.
Okay, thank you, Alice. And our next speaker is, and the last speaker, I think, Gabriel Granveau.
Okay. Hi, first of all, thank you for the opportunity to talk. So I'm Gabriel Granveau, I'm a PhD student at Lidice, and I'm interested in measuring density matrix of the electrons. So this work is part of the wavepackets collaboration with SCPNR. Okay, so as I said, I'm interested in measuring density matrix. So here I've covered density matrix of the electron, which is a function of two energies. You can see here. We see okay, so in the middle, that's the equation, so that's the probability of measuring the electron at the given energy. So that is measurable just with put it on spectroscopy. Again, there's the bars to the left and the right, the charge currents, and the equals the capability of two stages to relate with one another. So we can measure load with bit measurements, binding measurements, and allowing position from states. So that means by measuring plates and contrasts, we can measure this. But there's this part here that we can't measure. So if you want to know the entirety of the density matrix, and very important that you have to do so. Okay. So for this work, we're doing some theoretical framework. So if you use CUV alone to generate states, the states of the whole system will be described by this function, where we have these parts describing the particular value of the electron, and the rest describing everything else that we don't measure. And we have different channels that are represented by the vector. And from that, we can compute the density matrix, and especially the density matrix of the electron. It's associated with the A and K, and the wave function of the electrons. Whenever the infrared laser, and if we assume that the infrared interacts only with the electron and not with the vertical elements, the new wave function in this formula, where the charge fire will be some operator until only the wave function of the interaction with the infrared. Okay, so we can measure a spectrogram, but it will depend on the kinetic medium to measure, and some parameter tool that is the delay between the unit and the infrared, and it just the span of the collection of that to be constant state associated with this equation. And we can use this one for the equation class, and we can show that it will be equal to this formula where T is temporal with packets relative to the energy spectrum of the packets, and G will just be the equal rate between the number of ionization and so this is in time control space, but we can rewrite the equation, but you see the formula in the frequency space. So here is the energy spectrum of the direction, and choosing that is just the equation of the things. And the nice thing with that is that we can kind of find the formula for the complementarity and this is relating to the function of the local phase. And so the question of that is that we could take some continuum states using the SUV, and then the addition of the infrared will spread it like different continuum states. And there's some nice structure, and we can find that those states much the transition is 1 to the right totals. And if we have if you could take just 2 unit states on the domain negative, then we can easily compute the spectrogram, and the probability of measuring the energy states that are the probability that the electron take the path between omega 1 and the plus the path omega 2 plus some cross products that depends on the so that's the association is from probability elements, that's what's measured. And that was given to the instruments. But if we add continuum on energies, we just to we can find without approximation, new approximation. This formula here, where we have the instrumentric matrix of the electron, so this and the same interference thing as before. And so, since I'm interested in measuring this from this formula, we know that the contribution to the spectrogram is of the density matrix is non-zero only if the interference term is non-zero. So, if we want to measure this part of the density matrix, we have to make sure that the interference term is non-zero. So, we have to study this function. Also, another note is that this formula here, so which is equal to this, is very general. So we have this using distortion with approximation, but in reality, we can find something the same thing, only by assuming that the increment interacts with the electron and only the electron after ionization. Because we could use other approximation of this to be more risky. So we in the square I've plotted the integral of this interference term. And so the interpretation of this integral is that if it's zero, it means that for every energy investment, the interference term is always zero, and so there are no interferences between omega 1 and omega 2. And so the part of the density matrix between omega 1 and omega 2 does not contribute to the spectrogram, and so we can retrieve any information about this one. And if it's non-zero, it means that for some energy, the interference term is non-zero, and so the density matrix contributes to the spectrogram, and we can retrieve. And so we can see. So here we put in line arts of this function as a function of magnitude. So when you can see that it's made of like spikes spaced by measure 1 photon. And so in the spikes there are a lot of interferences, and so we can see that when omega 2 minus omega 1 is equal to 1 photon, there are a lot of information about this part. But if it's half photon, means that there are not much information, and we can't really retrieve information because and same if we go far, that we have very difference between omega and omega 1. Somewhere there was so again, I've got the integral. Here I've got the density matrix, and when it's large, it means that this function is almost zero, and when it's not large, it means that it's above zero, and the rest as well. And so we can see that for this density matrix, every part where the density matrix has some information, this function is non-zero. So if we measure the spectrogram of this generated with this density matrix, we could reconstruct it because all of the information will be encoded in the spectrogram. If this part was black, we could not retrieve information about this part, so we would not be able to reconstruct the density matrix. So I've plotted the line out again, and we can see that it depends on the parameter of the interactivity that we. So, for example, in yellow, we use a budget for 1.5 and when we increase the intensity to 4, we can see that the spike degrades that higher intensity, and we also allow transition from more back. So we have more information about this part of the density matrix, and we have information about these parts that we didn't have. So controlling the shape and the intensity of the interactivity is really important to make sure that we have avoid information. Okay. So one thing we'd like to try in the imaging the things about the displacement of the so there are two different channels. And
And so with one harmonics, we'll get two states here, and we want to know if they are congruent. So we want to know if this part is not zero or not. It should be zero. And with this course of 40 hours passing as well, and 6 seconds, this part here, it should be zero in the receiver. But it didn't get to short here, right? So this part here is covered by the information, so we should be able to measure the currents about it. And it should be zero in the okay, so the resistance to matrix electron is like contributes to this spectrogram, not only the population but also frequency. We can use the Ritzler algorithm, for example, to retrieve these matrix, and we can know which mark of the matrix in the equivalence. So the next step would be to quantify the information that we get to see if we lost the
Thank you, Gabriel. Yes, questions? When is the measurement?
Well, we have some trouble with laser and others. Hopefully, just maybe during the summer.
Play, right?
Sorry?
You want to play?
Yeah, yes.
I thought there are enough plays. Hey, Carla, do you want to?
Yeah, I think it's back to Coulomb. I don't know. I'm not going to ask anything. But thank you all for your great knowledge. So I'm not going to ask anything. I'm totally wiped up. So yeah. Hello. Okay, now it's on. So I'm not going to ask anything. I'm totally wiped out. But it was a great talk, as every talk in this conference. I really appreciate the effort everybody has made into coming here. We also appreciate the patience sometimes, because a lot of things were novel, but novel things work sometimes, sometimes they don't. So we appreciate also your patience, and we hope you continue supporting our initiative. We'll try our best to continue with this. No?
Years time at Belfast.
Yeah, maybe 3 years time in Belfast. So we keep in touch. If we recovered, we don't know yet. First one was online, second one in UCL. We are a team. And I think the quantum battles are not only about having a conference, but also about being disruptive in the best way we can about research culture and science as well. So thank you all for supporting us, and I wish you all a great journey home on behalf of all the organizing committee.
Thank you.